Continuing with the component level review of this motor drive schematic that I've been working on. And this review has been very productive in terms of finding different types of faults, which are easy to miss when first laying out the schematic. So I think that it's very productive to do a review component by component. And today I'm not really motivated to do any more reviews, but I think what I could do is review the op-amps, because that will allow me to greenlight a lot of lines in this document. So this is the document that I've generated from the schematic, and it contains all the components that are on the schematic. So the op-amps that I'm going to be reviewing today is the TLV2474. It's a rail-to-rail op-amp, and it's rail-to-rail both in terms of the inputs and the outputs. So some op-amps can be rail-to-rail in terms of outputs, but they accept inputs that are not rail-to-rail. But this one seems to support both rail-to-rail inputs and outputs, which is exactly what I want for this application. So I'm going to go and open this this data sheet for this component. So I'm going to go to this to Mouser, and I'm going to search for this component and open the data sheet. Let's see. I wonder kind of what would be faster, to just search for this component in Mouser, or to right-click and open properties and then open the data sheet. It seems to me that I've already started looking for this component in Mouser, so that's what I'm going to do. Okay, let's see. And sometimes Mouser just opens this. Sometimes the search term doesn't seem to be accepted for some reason. So I get like all of the components, 4.4 million components. So, are we getting anywhere here? Come on. Yeah, that was better. So this is the, let's see. So CDR, that's the one that I'm gonna be using. Let's see. 1,390. That's not that many, but luckily this type of pinout and this type of package is very common among op-amps, so I could replace this op-amp with any other op-amp that meets the criteria. But for now, I will use this op-amp as long as it remains in stock by the time that I'm done with this board. So I'm going to open the data sheet for this op-amp, and I'm just going to double check that we have the right footprint and the right pinout. So what I could do is actually go to U16. Which one is U16? Oh, that was U16. So each chip contains 4 op-amps. Let's see here. And where is the pinout? Let's see. Package pinouts. TLV2474. It's a 14-pin package. So we got SOIC 14, 3.9, 8.7. And do we have any footprints? Got, let's see. we have any? Let's see. There should be dimensions somewhere. Let's see. Where are the dimensions? In terms of the bandwidth, this op-amp should be fine because we're going to be amplifying around 30 kilohertz. So this should be just fine. Let's see. Is there any package description? Okay. Maybe this turns up some results. Okay. So where are the dimensions? Kind of hoping that I can find this PWP package somewhere. Okay. So where is the package description? Okay. Package drawing, D. So where are the package drawings then? Oh, there we go. There we go. So package drawing D. There we go. That's the D. Yep. So what we have to do here is just make sure that this package is correct. So we have SOIC14. And I'm gonna go to the package footprint editor. Let's see. So 5.4, and what is the... Okay, yeah. So that's probably going to be 127. Yep. and 5.4 here. Yep, 1, 2, 3, 4, 5, 6, 7, and then yeah. So package is fine. Next is the pinout, which would be up here. So 1 is number 1 out, 2 is in negative, 3 is in positive, 4 is VDD, 5 is 2 in positive, so that will be B. 5 is 2 in positive, 6 is 2 in negative, 7 is 2 out, and 8 is 3 out. C, 8, 3 out. 9 is 3 in minus, and 3 in plus, and then G and D is 11. And 4 in plus is 12. 4 in minus is 13, and 4 out is 14. That seems good. Now this will be, since this is negative feedback, it's going to be 1.5 gain, because the gain is this resistor divided by this resistor plus 1, which would be 0.5 plus 1, which is 1.5. So anything that is that comes out of here, this is going to be at most 3.3 volts. It's going to be multiplied by 1.5, and of course the voltage cannot go above the supply voltage of this amplifier. But then, since this amplifier is a rail-to-rail op-amp, the voltage will be hovering between slightly over 0 and slightly below 5 volts. Now, there are many op-amps that are not rail-to-rail, and that would make the output go to at most maybe 1 volt below the supply voltage, which is not what is desired in this case. So each one is pretty much the same section. They're all connected to this digital potentiometer, which regulates the voltage on this output. And this is designed for slower speed analog outputs, like kind of like emulating a joystick. So they're all the same, and then there is 5 volts on all of the 5-volt connections there. So I can green light this one, and 4 of them will just become green. And then we have U26. Why is there no U26? Is there no U26? Okay. Oh, right. So what we have to be looking for is U26A. Right. So U26 is responsible for amplifying the voltage on the so the VMOT, and VMOT can go up to 60 volts depending on whether the motor is braking or not. And let's see, so VMOT is also connected behind this diode, so the voltage can rise here above the supply voltage. And these sections are just connected according to the recommendations for unused sections, and the recommendation says that you should connect, you should float the positive input in between, like at half of the supply voltage, and you should connect the output to the negative input. And this makes sure that the op-amp chip itself remains stable. Now the supply voltage here is 3.3 volts. Let's double check also that the op-amp can work at 3.3 volts, which I think it can. I'm pretty sure it can work at 3.3 volts. 2.7 volts is the minimum supply voltage, so yes. And then we have this one will go to VMod Sense, yeah, and it's basically just we can just greenlight this because this is pretty much self-explanatory. I'll review the labels a bit later. I'm gonna do it as a separate step. So next would be U3, so I can search for U3A. And this is the analog input, and the purpose of these op-amps is to amplify the input signal such that we can then just use a resistor divider before feeding it into ADC, and to make sure that we can connect any resistance in terms of, if we connect it like a potentiometer here, it can be any resistance and we don't have to calibrate it. So this op-amp is protected at the input against any voltages that are slightly above 5 volts. Is driven by 5 volts, and the 5 volts that comes out here is translated to 3.3 volts, and the input is the current is limited by this 10k resistor. Now the resistors here are just to allow a little bit of experimentation so that we can adjust the gain if we want to, but by default it's just a 0R resistor. Each section is exactly the same, and let's see, we're using A, B, C, D, so we use all sections in this chip, and we can just greenlight this chip. So U3 becomes green, and U33. Let's do U4 first. Let's see. So U4, let's see, U4 goes here. A, B, C, D, and they're all the same. Now, yeah. So these two resistors, this one and this one, they are marked as no fit. And this resistor is just to be able to bypass this connection if we want to test that, and this resistor is used for the possible gain adjustments. So pretty much everything is the same, and then this connects to this multiplexer, and this multiplexer then goes to a single ADC pin on the microcontroller, on the STM32. So we can greenlight this one as well. U4. And finally we have the U33. U33A. And the purpose of this circuit here is to amplify the voltage on the back EMF voltage. So what happens here, or at least what is intended to happen here, is that we have this first section. Let's just check the sections first. So we have 33 A, B, C, and D, and we have 35 A, B, C, and D. Now I don't think we have. Do we have 35? U35. Right. So previously this was done a little bit wrong. So we only had U35A, I think, connected or something. We'll assume that when we greenlight this, we have greenlighted all of them. So we have the first section generates half of the voltage, so it will be half of 3.3 volts. Now, and then this output at half of the supply voltage is used to provide the offset for the measured signal here. And we don't have to worry about any effects of these resistors that they may have on this resistor divider, because we are feeding it through the op-amp, and then the same signal is kind of fed to all of them, which may be a problem actually, but I'll have to investigate that actually, but I don't have time to do that now. That could be a problem. Maybe I should feed it somehow through some diet or something. I don't know. I don't know yet. I have to think about that. Yeah. So maybe I cannot greenlight this right now, actually. What would be the best solution for this? To make sure that the offset is not affected by, so that the inputs don't affect each other. I think that one solution that I will try is actually put in diodes here, and then I'll have to simulate that and just make sure that that it works as intended. How long would it take to draw this diagram? Let's see. Let's close these ones. This was my previous simulation of the analog inputs. And this was using LM358, which by the way was not a rail-to-rail op-amp. Let's see. At least not on both input and output. What could this, let's see. Do I have the SPICE model for that op-amp? I think I do. No, I have TLV2371. Okay. It's almost that I have to do this now. Let's see. LM2474 SPICE model. Oh, TLV. I'm pretty sure I had this model somewhere, but where is it? Maybe it was in the voltage sensing. Yeah, definitely. So this was the model that I used for the voltage sensing. So maybe I can just let's see. So we have this offset here, but what we have to do here is just add a second op-amp here. see. So if I simulate this, I should be able to see that. Let's see. So then this one is offset by a small voltage, so it becomes it's brought above 0. But what is interesting here is to add another one here. Like, is there really no copy in the software? Let's see. How do you copy? Maybe I should have this selected. Let's see. Or maybe I can press this and then, okay. That's how you copy. Let's see. So we have, oh, wait. I have an idea. Can I do like this? Awesome. This is awesome. Finally, I figured out how to copy in Altispice. Okay. So you got that one, and this will go here. And then we have the positive one. So the positive one should connect to another one, another source like this one. So this should be 2 sources, and then let's see. Put a ground symbol there. And we should have a little bit of a time offset here, so if this would be let's make this a different frequency. Like this. And just copy in these resistors. Come on. Copy. Awesome. This goes here. Then this one will go this would be the signal for the second one here. Except it has to be passed through a 10K resistor, which can be placed here. And it needs to have a 10K offset like that. So the offset will go then from here to this 10K resistor. Damn it. Okay, let's see what this looks like. I don't think we're gonna see anything if we do it like this. I think it should be a square wave. 2000 hertz. Be 0, let's see, 0.000025, 0.0005. Zero, 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 20. Or actually, let's make this 25, and let's make this exactly the same frequency, but have a small delay here. 0.0001. Yeah, so there is a little bit of noise here. But the question is whether this noise is even noticeable. Because we've got a much stronger signal here, so any noise is kind of very minor. Yeah. Let's have a look at that one and this one. There's a very small kind of variation there, but in general it's just, it doesn't really matter. Let's see, how do I zoom out? Zoom to fit, okay. Yeah. Awesome. So we got 2.2 volts there, and it's offset to, although this one is offset to 1.1. Let's see. So I see. So there is indeed an effect here, because if doing it like this, or actually no, this, I think this was correct, because it's a square wave. So let's see here. So this seems to be kind of so what is the voltage here? 1.6, and then it becomes, yeah, okay, so it's offset to 1.6, like 1 point, yeah, so that becomes pretty much the middle, 1.65 something. And then the output becomes, Oh, I understand. Yeah, so I get it. I get it. The problem here is that the sinusoidal signal was actually moving below zero. So it was when it was being offset, it was actually moving down to zero, and the square wave signal is not going below zero, and that's why we are seeing this effect where we have the lowest value basically becomes 1.6 here. So this becomes the offset, which is intended. So actually, yeah, I think this will this has a pretty good chance of working. Of course, it might work differently in the real world, but I think I'll leave it like this for now, and then I can greenlight all of these op-amps. So I'm gonna go ahead and just mark all of them as well as that one. Alright, if you think that I missed anything here, then feel free to comment on this video, and until next time.